right, folks, let's jump into two-way slabs. This is kind of where we go from things that are somewhat challenging to somewhat quite a bit more challenging. But that's good because at this point we can handle it. You've got a lot of basics that we can apply to this and start to understand things. So one of the keys with flat slabs is they're much more sensitive to what we call punching shear failures at the columns. Because there's no beams, there's no depth to the beams, these types of structures tend to lack some of the robustness that a cast in place beam type project would have. Now that doesn't mean that we can't make it work, we just need to be more aware of what's going on and design for the things that matter. Alright, so one-way versus two-way slabs, kind of a definition. I'll let you kind of dive into that. One-way slab design, basically like beams. The bending design is done just like a beam. Shear design would be one-way shear. Chapter 7 in the current ACI would cover that for you. Two-way slab systems, there's a variety of types. Flat plate are very desirable in hotels because they tend to limit the floor-to-floor heights. You see flat slabs with drop panels or capitals in some of the older school buildings. We still do those as well. Waffle slabs, the University of Utah's architecture building is a great example of this. I think they're elegant and very efficient. And then two-way slab with beams, where you have beams on grid and slabs spanning two directions between those. A little bit on the slab failure. What these basically are telling us is there's a lot of redundancy in these types of slabs. Variety of analytical methods. It used to be that ACI 318 had the direct design and equivalent frame methods. Those were taken out in 2019, mainly to catch up with the fact that finite element analysis has replaced pretty much all of these methods. The direct design method has very strict rules on how you can use it or limitations. And with finite element analysis, you really have no limit on geometry, loads, etc. All right, so some general steps. We want to start with the general configuration, then jump into the slab thickness, and then choose the analytical method. We'll talk about each of these and get into all of this as we get into this. All right, so first, the code has minimum thicknesses for non-PT slabs, and they're going to be a function of primary reinforcing. Do you have drop panels or not? Are you in an exterior or an interior location? And then L sub n would be the span taken face to face from the columns. And if you don't know your column sizes, maybe start around 16, 18 inches, and you're probably in a good place. Finite element. So most, I'm not sure what word to use, but a great way to do this is a FEA model. We want to pattern the live loads, assuming that our live load is more than twice the dead load. The McGregor book, or the white book that we have listed, basically says if your live loads are not more than double your dead loads, the pattern live load effect isn't that big of a deal. And then any other loading or pattern loading that may not be in the code, the code's really a general guide. You may have a situation where loads are different. You may have equipment loads, heavy point loads, things like that. Another key thing is to use the cracked moments of inertia from the code, because ultimately that's what will give us a more realistic stiffness in our analysis. So on a flat slab, the moment of inertia factor is 0.2, whereas for a column it's 1. So that's important to use that pretty much for everything when we're doing finite element models of concrete. All right, direct design method, a variety of steps. Listed here, I've included notes on this mainly as a way to check your finite element analysis calculations. So kind of the general concept is we'll take what's called the static moment, which is a function of the factored uniform load, times the span in the direction we're not saying we're spanning for this example, and then L squared for the span over 8. So you can see there's some familiarity of that to just a WL squared over 8 type analysis where Q times L2 would be W. Once we have that static moment, we're going to spread that into both a column strip and a beam strip, and then also positive and negative moments. So first we're going to do it, take this moment, split it into positive and negative moments, and then apply that into what's called a column strip, which gets more moment, and a middle strip. All right, so kind of some geometry definitions based on the lengths. So if we have L2 is less than L1, so the primary span is L1, then this column strip is defined as L2 over 4. And then if it's greater, then L2 is greater than L1, then we're L1 over 4. Okay, from there, we're going to say in an interior span, 65% of the moment, static moment, goes as negative moment, 35 as positive moment. If we're an exterior span, it's a little more complex. And then from there, we're going to take that negative moment, and if we're an interior span and we meet certain ratios, then we're going to say 75% of that, or 90 or 45, depending on what these ratios happen to be, go to the column strip. So generally, a lot of the moment goes to column strip, and then what's left over goes to the middle strip. So anyway, I've given you an example in Canvas of the direct design method, where the author walks through step by step, and White does a great job on their entire book's excellent. This is a great example on how to calculate the static moment, come through, start distributing those moments into the slabs. All right, I think that's enough for that. I don't want to get too far into that because my preference would be that you use a FEA model to do this analysis. Little figure from the code on how to proportion the rebar, or where you can cut off the bars based on moments and forces. So there's a top bar. 50% of the minimum still needs to be like this. The remainder can be like that. The bottom 100% of the still, at least 2 of the bars needs to be hooked, and then the rest can extend into the column 6 inches. Remember, the bottom, the moment's the biggest at the middle, and then the top and the slab, the moment's the biggest at the top. Anyway, all right, so let's talk about something that's pretty dang important and kind of gets to this punching shear failure thing. So when we have moment transferring into a column from a slab, it happens in 2 ways. The first is pure bending, where you have a tension and compression couple that transfers those forces into the column. The second way is, you can imagine, if you will, this plane that's shown with the arrows on it has 4 sides acting or having a bending moment on it, and instead of creating a tension and compression couple, it creates shear stress. So on one side, as this moment cranks down, it creates shear stress. On this plane, it diminishes to at the centroid of the column, and then shear stress in the other direction and on this back side that we can't see very well. That additional shear stress due to the moment transfer can cause punching shear failures. So it's something we need to design for in our structure. And this is a key thing that I want you to do in this submittal. Okay, so how much gets transferred of the moment, how much gets transferred through this pure bending versus sheared? So we have these equations that walk us through that. I'll let you do that for your finite element analysis to get this number. What I'd like you to do is load one side of the slab and then not the other, and then load all the slabs and see what the difference in moment transfer is at the column, which really should be not much, if any, with the fully loaded option. The other option is to use this type of equation to do those calculations. All right, a little bit on shear, punching shear. This diagonal D would be the one-way critical shear at a corner. You have one-way shear here, and then you have punching shear at all the other columns, including this one. All right, so as far as the two-way shear goes, if there is no unbalanced moment, we design it just like footings. And then if there is unbalanced moment, we'll consider the moment transfer as a tension compression couple, and then also through shear like we just talked about. So some more images of what this looks like. So the pure shear is given here, and you can calculate the punching shear stress as the shear demand divided by the critical perimeter times the depth D. And the shear stress due to V sub U is given by this equation. We'll talk about it here in a second. So when you combine these two stresses, you end up with a shear stress distribution that could look like that. Let's take an example of an exterior column where we don't have a back edge here or a back continuous slab. Then we have a shear stress due to vertical loads like this, a bending shear stress like that, and a shear stress distribution that looks like this. And what we really want to do is calc the shear stress at the maximum here, compare that to our punching shear stress, and understand what's going on that way. All right, so this will walk you through a little bit more of what's going on here as far as the nuances. So here we have the shear stress at line AB, which is going to be right along here. And that's going to be a function of the vertical force and the moment transfer through the slab. And this J sub C is the polar moment of inertia of our critical shear perimeter. Okay, so this table here will give you the J over C. This is not J sub C, this is J sub C over C. And you can kind of play around as you get into this, what your geometry is, what your parameters are, and kind of start calculating the parameters or the coefficients that plug into these equations. All right, they kind of get burly, but something you guys can handle. All right, so again, we're going to calculate these shear stresses due to, I thought I had another figure, I guess not. We're going to calculate these shear stresses due to a combination of the vertical shear and the shear from the moment transfer into the column. All right, if our concrete slab doesn't have the capacity we need, then we can use different types of slab reinforcement. So this is a plan view where we have a column and then some kind of horizontal bars that really are in place as much as anything to carry or to hold those in place, the stirrups in place rather. Anyway, so you can see the stirrup right there. All right, another thing that's very common these days are stud rail, where you basically have a piece of flat steel bar and these large headed studs that are welded onto it, and those do the same thing as these tied bars. These are very common in post-tension slabs, which this is. You can see the mild reinforcing, which is code required to give some kind of load carrying capacity. And then the tendons you can see running through here. Where are those guys? Actually, I think I speak with forked tongue because I don't see any tendons in there. So it looks like this is just a mildly reinforced slab, or it's a post-tension slab that the tendons haven't been placed yet. Anyway, so there you have that. And then lastly, a drawing example of how the stud rail would be shown in practice and called out. So anyway, enjoy that. We shall talk more. As far as resources, I've given you this example. There's an example for the shear transfer. Something looks out of order there. I'll have to fix this if there's a problem. Oh, here we go. So anyway, this example walks through all the shear stress type of things at the face, or the interface we were just looking at. All right, enjoy that. The quiz is up and ready, and we shall talk more. And just as a reminder, there's other resources in your ACI 318 Plus subscription that I encourage you to take a look at if you're feeling a little shaky on any of this. And if it feels hard, kind of stick with it, because this stuff pushes into some more challenging areas of concrete design than some of the stuff we've done so far. All right, talk to you later.